Alright, welcome back everybody. In this video we're going to look at relative growth rates of functions and how we can use L'Hopital's rule to help us determine relative growth rates. Make sure you read through the first page of information on the relative growth rates because that gives you kind of some insight into how we're doing this. Alright, so we want to determine which function grows faster, e to the x or x squared. What we're going to do is we're going to take the limit of the ratio of those as x goes to infinity, and then depending on what happens, that'll determine which of these two functions grows faster. Alright, so when we set this limit up, we have a limit of the form infinity over infinity. So we're going to apply L'Hopital's rule. The derivative of the numerator and the derivative of the denominator. And we still have infinity over infinity. And so this is equal to, we apply L'Hopital's rule again. We get e to the x over 2, which is infinity over 2. And so this limit approaches infinity. Since the limit approaches infinity, the function that's in the numerator of our original expression grows faster. And there are really three circumstances that can occur here. We can have this limit approach infinity, in which case the numerator grows faster. We can have the limit be 0, in which case the function in the denominator grows faster. Or we can have the limit be some finite value, something between 0 and infinity, really anything between 0 and infinity. And if that happens, then the two functions grow at the same rate. Alright. Some more information there along the way. Example 2, we're going to show that f of x and g of x grow at the same rate by showing that they both grow at the same rate as h of x equals x. So first I'm going to compare f and g. So we've got those two functions, which is infinity over infinity. So I apply L'Hopital's rule. And this becomes 1 over square root of x squared plus 5 times 2x all over 1. Gosh. And so let's see. Oops, I forgot my 2 here. And so simplifying this becomes the limit as x goes to infinity of x over the square root of x squared plus 5. Which is still infinity over infinity, but what I notice here is that these two are reciprocals of one another, and I feel like I'm going to get caught in an endless cycle of applying L'Hopital's rule. But since those two are reciprocals of one another, that means that their limits are reciprocals of one another. And since they're equal to one another, that means that this limit has to be equal to 1. That's the only number that is equal to its own reciprocal. So we've shown that f and h grow at the same rate. And now we're going to do the same with g and h. We'll take the limit as x goes to infinity of 2 square root of x minus 1 quantity squared over x. And we'll apply L'Hopital's rule. So this is the limit as x goes to infinity of 2 times 2 square root of x minus 1. The first times the derivative of the inside. The derivative of 2 square root of x is just going to be 1 over the square root of x. And the derivative of our denominator is 1. And so this becomes the limit as x goes to infinity of 4 root x minus 2 all over the square root of x. And so we've got still infinity over infinity. We apply L'Hopital's rule again. And the derivative of the numerator becomes 2 over the square root of x. And the derivative of the denominator becomes 1 over 2 square root of x. And so, simplifying this a little bit, this becomes the limit as x goes to infinity of 4 root x over root x. These cancel, and so that limit becomes 4. Alright, so g of x and h of x grow at the same rate. Therefore, because of this, and this, and the transitivity of growing at the same rate that we see from Theorem 2, we can conclude, therefore, f of x and g of x grow at the same rate. Alright, let's move on to example 3. We want to order the functions e to the 2x, x to the 9th, 3x to the 8th, 8 to the x, and natural logarithm of x quantity raised to the 3rd from slowest growing to fastest growing as x approaches infinity. And we can kind of put some of these in order without a whole lot of thought. But generally, if we get stuck, we can always use the limit as x goes to infinity to find the relative growth rates of these functions. So for instance, which one grows faster? E to the 2x or x to the 9th? And this is infinity over infinity, and we could apply L'Hopital's rule a ton of times here. And we keep having this e to the 2x in the numerator, but the denominator would get smaller and smaller and smaller and smaller in power. So we know that e to the 2x grows faster than 9x to the 8th. So we know that. We have those two in order. Alright? And then we can compare 3x to the 8th to x to the 9th. Which we can actually reduce right off the bat to 3 over x, so which goes to 0, and therefore x to the 9th, I wrote the wrong thing, it goes faster than x to the 9th, that was the function we were comparing it to. X to the 9th grows faster than 3x to the 8th. So at the very least I have now these three in order. I want to compare 8 to the x. Now, since that's an exponential, my first gut instinct is compare it to e to the 2x right away and see where it fits into the hierarchy. So limit as x goes to infinity of 8 to the x over e to the 2x. And really, e to the 2x is e squared, whatever that is. So the question becomes, is that bigger than 8 or not? Because when I take the derivative of this, or apply L'Hopital's rule to this, I'm going to have 8 to the x, natural log of 8, over 2e to the 2x. So the question is, are these getting bigger or smaller? And it's all dependent on whether the natural log of 8 is bigger than 2 or not. The natural log of 8 is slightly bigger than 2. And so this ratio grows a little bit each time, which means it's eventually going to go to infinity. So 8 to the x grows faster than either 2x. And hopefully as you do more and more of these comparisons, you'll see that there are some easy ways. You know, for instance, when we look at polynomials, the larger the power in the polynomial, the faster it grows. When we look at exponentials, the larger the base of the exponential, the faster it grows. And so we've got this hierarchy, and we only need to figure out one more thing. Where does the natural log of x to the third fall? Let's compare it to the smallest one. You know, limit as x goes to infinity, the smallest one that we know so far, which is 3x to the 8th. See if this falls at the bottom of the hierarchy or elsewhere. And if we find this limit, we'll see that this limit goes to infinity. I'm not going to go through all that process because I'm kind of running low on time here. But we'll find that that approaches infinity, and therefore 3x to the 8th grows faster than natural log of x to the third. So to order these from slowest to fastest, we've got natural log of x to the third, then 3x to the 8th, then x to the 9th, then e to the 2x, and then 8 to x. And I put that last parenthesis in here. There it goes. And so there they are in order from slowest growing to fastest growing. One more quick example. Which grows faster, x minus 4 to the third, or 2x plus 3 plus natural log, 2x to the third plus natural log of x? If we compare these using limits, we've got infinity over infinity. We apply L'Hopital's rule. It gives us 3x minus 4 to the second over 6x squared plus 1 over x. And now I'm going to do something kind of clever here. Notice that this piece approaches infinity as x approaches infinity, and this piece approaches infinity as x approaches infinity. But this piece right here approaches 0. And therefore, as x goes to infinity, it's going to be inconsequential. And so this limit is equal to the limit as x goes to infinity of 3 times the quantity x minus 4 quantity squared all over 6x squared. So a little glitch there. And so I can continue rolling L'Hopital's rule on this. And this becomes 6 times x minus 4 to the first over 12x. And apply L'Hopital's rule one more. That's still infinity over infinity. Apply L'Hopital's rule one more time. Oops, sorry about that. And we end up with 6 over 12. So this limit is 1/2. So which grows faster? They grow at the same rate because we got a finite non-zero value. Okay. All right. That's the end of this video on the examples of relative growth rates. See you guys next time. Have a great rest of your day.